Hello, and welcome to my Fate and Transport presentation. I'm Jeremy, and today I'll be talking about hexavalent chromium contamination in Hinkley, California. Before diving into the specifics of Hinkley, let's first address the chemical at the heart of this issue, hexavalent chromium, also known as chromium-6. I'll be using them interchangeably in this presentation. Hexavalent chromium is a highly toxic chemical and known carcinogen. Chronic exposure through ingestion, such as in drinking water, can result in liver damage, intestinal tumors, damage to the reproductive systems, and stomach cancer. Now, let's move to where the story unfolds. Imagine it's 1993 and you're in Hinkley, California, a small, rural town in the Mojave Desert with a population of just over 3,000 people. 3 years later, the residents of Hinkley sue the Pacific Gas and Electric Company for $333 million, one of the largest class action lawsuit settlements in U.S. history. And now, today, Hinkley has a population of less than 1,000 people, a third of what it had back then. So, what happened? How are hexavalent chromium and Hinkley connected? Let's step back to the early 1950s. Pacific Gas and Electric Company, or PG&E, constructs a compressor station near Hinkley to distribute natural gas across California. To prevent corrosion in the cooling towers, they use hexavalent chromium and then discharge this wastewater. But they discharge this wastewater into unlined detention ponds. This goes on from 1952 to 1966, and in that time, PG&E dumps 370 million gallons of wastewater. As we'd expect from the knowledge gained in this class, this wastewater proceeds to seep through the soil and into the groundwater. Hexavalent chromium is soluble in alkaline oxic water, which also happens to match the groundwater characteristics in the Hinkley area. Fast forward several decades of improper disposal practices, and the contamination plume has spread through the groundwater, which supplies the town's drinking water through wells. Hinkley residents are found to experience unusually high rates of cancer, respiratory problems, and other serious health conditions linked to chromium-6 exposure. Ensuing investigations into these health issues results in the discovery of PG&E's historic dumping and groundwater supplies contaminated with hexavalent chromium. In response, a landmark class action lawsuit is filed against PG&E. As previously mentioned, this case concluded in 1996 with a historic victory for the residents, resulting in a $333 million settlement and a mandate for PG&E to begin cleanup efforts. Fast forward to 2000, and the Oscar-winning film Erin Brockovich is released, which tells the story of the legal clerk that helped bring attention to Hinkley. This movie brings mainstream attention to the Hinkley story, and this dramatized version paints a hopeful picture at its end, where the residents use the lawsuit money to rebuild their lives and the contamination is fully resolved. It's a satisfying Hollywood ending, but the reality is unfortunately far more complicated. In reality, Hinkley's groundwater remains contaminated and remediation is ongoing. For further context, in 2023, the USGS concluded its study on the background levels of hexavalent chromium in Hinkley's groundwater. While chromium-6 can naturally occur due to the area's geological makeup, this study aimed to provide a more accurate baseline and to supersede PG&E's original analysis conducted during the lawsuit, due to locals' distrust of that original analysis. Similar to how we discussed tritium dating in class, the researchers used uranium and radioactive isotopes to trace and date the natural background levels of chromium-6, and this allows them to determine the concentrations of hexavalent chromium before the contamination plume entered the groundwater. This updated study revealed that the extent of hexavalent chromium released from the Hinkley compressor station is actually larger than earlier estimates, reshaping the understanding of the contamination and its impacts. And so, regular updates to plume maps are critical for understanding how the contamination is spreading, evolving, or stabilizing. This helps guide remediation efforts and ensure regulatory compliance. The figure on this slide here shows the latest extent of the hexavalent chromium plume in May 2024. Back in 1993, this plume was near residential areas and wells, but today, much of those residential areas have been bulldozed, which I'll talk about later. Currently, PG&E's remediation strategy has focused on reducing rather than removing the hexavalent chromium contamination. The goal is to chemically transform hexavalent chromium into trivalent chromium, which is non-toxic and much more stable in the environment. On the slide here, you can see the reaction at the heart of this process. By adding a reducing agent, chromium-6 gains electrons and becomes chromium-3. This approach of reduction is more cost-effective than straight-up removal and leverages various processes to stabilize the contaminant. One of these remediation processes is through alfalfa. On the outskirts of the chromium-6 plume in Hinkley, pumps draw water from low concentration areas to irrigate fields of alfalfa, a crop now covering much of what used to be the town of Hinkley, as seen in this photo here. Through natural biochemical processes, these alfalfa plants take up chromium-6 and convert it into the non-toxic nutrient chromium-3. This technique prevents the plume from spreading further and acts as a practical, nature-based solution to managing contamination. However, in areas with higher concentrations of chromium-6, in situ reactive zones, or IRZs, come into play. You can see an example diagram of what it looks like on the slide here. These zones use a water ethanol mixture that's pumped into the groundwater to stimulate naturally occurring microbes. These microbes then consume the ethanol, which lowers the pH and creates conditions for chromium-6 to be reduced to the safer, non-toxic chromium-3. However, as mentioned earlier, no chromium-6 is physically removed from the groundwater through this process. This technology is used globally and has been deployed at full scale in Hinkley since 2006. Around the compressor station, there are still hundreds of monitoring and treatment wells in Hinkley, as well as chromium-6 levels in this area can exceed 1,000 parts per billion, which is over 100 times California's maximum contaminant level for hexavalent chromium. However, these remediation strategies have limitations. While reduction is effective, it doesn't physically remove chromium from the groundwater system, which means that under certain conditions, like changes in pH or redox potential, chromium-3 could reoxidize back into the toxic form. Laboratory experiments have shown that if dissolved oxygen re-enters groundwater, the reduced trivalent chromium could reoxidize to hexavalent chromium. As a result, this emphasizes the importance of long-term monitoring and management of Hinkley's groundwater. The pollution in Hinkley has also had broader implications, highlighting environmental justice issues, regulatory challenges, and the impact on the community itself. First, Hinkley has served as a powerful case study in environmental inequity. As a rural town with a predominantly low-income population, Hinkley was particularly vulnerable to corporate negligence. Limited resources and weak regulatory oversight compounded this issue, leaving residents with few avenues for justice. In addition, the community lacked access to independent water testing or medical expertise to challenge PG&E's initial assurances. This underscores a broader pattern where marginalized communities disproportionately bear the burden of environmental hazards, often exacerbated by power imbalances between local populations and large corporations. On a regulatory level, Hinkley's contamination spurred stricter standards for hexavalent chromium, with the California government initially setting a maximum contaminant level, also known as an MCL, of 10 parts per billion in 2014. This regulation, though, was later overturned by the California Superior Court in 2017 due to concerns about economic feasibility. For example, implementing the necessary treatment methods to reach this MCL could be very costly for water treatment facilities, particularly for smaller or disadvantaged communities. However, as of this year, the maximum contaminant level has officially been reestablished at 10 parts per billion after considerable documentation and review. And as for Hinkley itself, it's important to recognize that Hinkley has truly never recovered, despite decades of remediation efforts. The contamination not only altered the physical environment, but unfortunately dismantled the community itself. Many residents relocated after the contamination came to light, leaving behind an area that has virtually become a ghost town. As I mentioned previously, PG&E bought up a majority of those houses from departing residents and bulldozed them. For those residents who remain, community involvement continues through remediation workshops and groundwater monitoring initiatives, though many of the community members remain suspicious. The legacy of this contamination highlights the long-term challenges posed by industrial pollution and underscores the importance of addressing such issues. Hinkley particularly serves as an invaluable case study for those of us scientists and engineers in environmental management, highlighting the complexities of balancing industrial development with the protection of environmental and public health. And that is it for my presentation. Here on this slide, you can find the references that I used, and on this slide is credit to the presentation theme that I used. Thank you.